Okay, so we're going to talk about stacks, and you've already been exposed to the concept of, you know, making function calls, pushing things on the stack, popping things off the stack. I think you've seen that in your coursework prior to this, but we're going to break that down in a much greater detail at this point. So, okay, so we're gonna talk about really two things. One is kind of this notion of static allocation. It's sort of a historical flashback, and then we're going to talk about kind of how we remedy some of the problems introduced by this historic approach. So historically, allocation of activation records was done statically. So the idea would be that you get one activation record for every function, period. And it's really quite simple, right? I take every function I'm ever going to do, I make an activation record, I do it at the beginning. And the original, kind of Fortran and COBOL did this approach. And it winds up being, really simple as you can imagine and super fast, which was critical at the time. The problem is that, well, what is the problem? Think about it. I'm going to show you a picture and then let's break down what the problem is. So here's a classic example. This is Fortran. You've got a parameter. We got parameters ARR and N. This is passed by passed by reference, so that I've got the address of N, the address of ARR, or I don't know what that stands for, array. I've got a return address, then I've got a local variable I, local variable sum, local variable average. You can see those. And there we go, there's my activation record. What's my problem? I only get one of those, so what can I not do? I can't do recursion. I can't do multi-threading. Gosh, would that be at all valuable? Yeah, it turns out recursion and multi-threaded are really, really important. So this is not, it's not viable, right? And actually at some point in the evolution of programming languages, it was pretty quickly, not viable to have this as a limitation built into the language, no recursion. So the solution is this notion of stacks, using stacks, okay? And this is what you're kind of familiar with at some level that you should have been exposed to at this point, at some point in your education prior to this course. And the idea is that in order to facilitate recursion, we've got to create a new activation record every time we get a new activation. And that allows me to have a function, call itself, call itself, call itself, and every one of those is generating a new activation record. So, I'm going to do that dynamically. And, the real question is, how am I going to do that? Where am I going to do that? Because what I mostly need to do, as you can see in kind of bullet 3, for many languages like C, we're going to deallocate it when the function returns. I'm going to allocate it and I'm going to deallocate it. Well, it turns out that if we actually create this stack of these records, push it on the stack, pop it off the stack, and we call these stack frames, okay? And again, this is kind of the traditional model. It's what you think of in sort of traditional, these days, traditional function calls. So, again, back in the day, you'd actually identify the activation record even before you were running. You would lay the thing out, and when you loaded your program, you had allocated space for that and things like that. You weren't even running it. But these days it's very much always dynamic. It's always that you don't know the location of an activation record until it's runtime, until you're in the middle of it. Okay. and that's for compiled languages as well as for interpreted languages. But the function's got to know, the function has to be able to know how to find the address of its current activation record. And, so there's some mechanism, and we'll show you a picture on the next slide. And, sometimes there's a register actually dedicated to that in the processor, right? But what you can see here in any case is right here. We're just going to conceptualize it and say there's some way for this thing to know the current activation record, okay? And in this graphic, it's just current activation record. And how we know, we're just going to call it magic for now. And there's a lot of implementation differences in precisely how that's done. But we're going to do two examples, and the first one is in C. So what we've got here is a function called fact. It's a factorial, okay? I'm going to take a variable n as a parameter. I'm going to declare a local variable of result. And the way this thing works is my base case, if n gets less than 2, then I set my result equal to 1. And otherwise, my result is n times fact n minus 1. Now that's the recursive call. And when I'm done, I return result, okay, which is, again, right there statically. Sorry, not statically. I mean, it's a local variable. And you can see the activation record right here. There's n, the parameter. There's the return address, and there's the previous activation record. And we're going to get to that later, why we care about, a pointer to the previous activation record. And then there's result, our local variable. Now what's going to happen is we're going to drop in here, n is 3. This is going to fail, so it's going to go here. And it's going to make a call to factorial with n minus 1. And that's what we see right here. And again, this is current activation record, which is now pointing to this guy. That activation record was just created dynamically. Factorial was called with n minus 1. That was n, so that's now n minus 1 over here. New activation record with n of 2. Return address, and a pointer to the previous activation record. See that? And we've got a local variable result that still doesn't have anything in it. Now what's going to happen? We're going to come up here. Is n less than 2? No. Drop in here. Result equals, we're going to call factorial n minus 1. Boom. New activation record. N is 1 in this activation record. I got a return address. I got the previous activation record. So you can kind of see this chain of activation records, which again is going to come back. At this point, what's going to happen is n is less than 2. So we're going to set result equal to 1. Result gets 1. We're not going to do the else. We're just going to return result. Okay? What's going to now happen is, boom, we pop back off. Now the current activation record, it's now at this point, remember it made this call to factorial n minus 1. It takes that result, which was, if you look back over there, 1. So this evaluates to 1. And this is, the activation record just shows these values. It doesn't show you all the logic, right, of the function. I'm going to take that, though, and I'm going to multiply it by n. So I'm going to take that 1 times that n. That's going to be 2. I'm going to assign that to result, stick it right there, and then I'm going to return result. That function now has ended. Boom. I pop back off. I've now, at the current activation is now here. Again, this function stopped right there after calling fact n minus 1. That fact n minus 1 evaluates to 2. That was what was returned, okay? So I got 2 times n is 3. 2 times 3 is, boom, 6. I got 6. I assign that to result, and then I return that value back, which is right here, factorial of 3 equals 6, okay? That's the C example of kind of how that nesting works with those activation records. The other thing I hope you get out of this is, as you start to look at doing the compiler, in the compiler class and trying to deal with conceptually how things are working as things are being pushed on the stack. This is a really nice description. These slides are a very nice description of that kind of maintenance of context as you push things onto the stack and then pop them back off the stack. And so now to kind of end this section, we're going to do an example in ML, okay? And this one's a little more complicated because we're doing this have, where we're going to, if you remember, again, this is one of those functions we've talked about in our ML programming. And we're going to do a have of 1, 2, 3, 4 as a list, okay? And what have does is it splits that list in half. It should end with a list containing 1, 2 and another list containing 3, 4, okay? So again, here's our function. Over here, it's going to stay there. There's the current activation record. We got the parameter. We're just calling it parameter, which is, we made this call, okay? Have 1, 2, 3, 4. And then we've got a return address. We've got the previous activation record. Now this is interesting and actually ought to give you a little more clarity in terms of what's happening when you're doing ML programming. Remember here I've got patterns. I've got, if it's nil, I return nil, nil. If it's only a single element, I call that A and I return that. Otherwise, if it's more than one element, I've got an A, a B, and CS. Well, notice right here, there's the A, there's B, and there's CS. And it's shoving these values taken from here and putting them into here. So A is 1, and B is right there. B is 2, it gets saved. CS is the rest of it, which is the list 3, 4. X and Y, I see and I allocate here in the let. And I don't actually know, if ML is going to do this on a block activation or if X and Y are created at the very beginning. This seems to be showing them, created sort of more at the beginning. And the value to return, I don't know what that is either. These are just allocated spaces and they're labeled. Okay, so that's where I'm at. And then remember again to look at this. These are easy. The two base cases are easy. But if I've got two elements or more, I get A, B, and then the rest of it. I set a value, which is a tuple of X and Y, and I have that equal to have CS. So I take that guy and I recursively call have. And what I do is I take the two halves and they're returned as a tuple of those two halves. Okay? And then my context is in A, so I've got A pulled out, and then X is half of CS. Then so it's right there. Then I got B pulled out as the second element, and then Y being the second half of CS, sorry. So I get B plus the second half, A plus the first half. And if you remember, I doubt you do, but if you do, this is how have worked and how it sort of, broke a list into two parts of roughly equal size, no more, off by no more than 1. So let me back up. So when I make that call of have, right, when I make this first call, I get CS is 3, 4, A is 1, B is 2, which means I'm in this pattern matching right here. The base case has not been reached. So I let val xy, okay, there's X, there's Y, equal have of CS. So I got to call have with CS. So CS, remember, was the list of 3, 4. Boom, that's it right there as the parameter. Have CS, there's CS, I called it, there it is. I got a return address, I got a previous activation record, pointing back to this record. I'm now going to go in my pattern again, okay? I now have a 3, 4. So do I match this first one? No. Do I match the second one? No. I'm back. I'm again back here again. I got A, B, and CS. So A, the first element, B, the second element, just like normal. CS is empty list, right? And I put those values right in there. I call have CS again. There I am. I'm calling have CS. Only CS is empty. So the parameter is empty, return address, previous activation record again. Now check it out. The parameter comes in as the empty list. Okay, that's going to match this one. It's going to match nil. Therefore, I'm going to return this tuple of nil and nil. Boom, there it is right there, nil, nil. That's the value to return. Okay, so I pop back off the stack. I'm now back at this activation record. Now notice that X and Y have values. Okay, because I did a have on CS. CS was the empty list. I did a have on that over here. It returned a tuple of 2 empty lists. One empty list became X, the other empty list was bound to Y. So X and Y are each empty lists. And then what the value I'm going to return is A appended to X, which is the empty list. So therefore, that list of just containing 3. B, same thing, only 4. So I've got this list of 3, list of 4. That's the value I return. Pop off the stack again. Now what's happening over here, by the way, at this point, you can start to see that, the half of this is going to yield 1, 3, and 2, 4. That's the result. But I finally got them right here. The value to return was the list of 3 and the list of 4. Okay. Again, the code is right here. I did half of CS. I put the first one into X, the second one into Y. So that first one, so X becomes the list containing 3. Y becomes the list containing 4. All right. And there we go. Now we're in this part here. A appended to X. There's A, there's X. So 1, 3 is the first one. And then I've got B appended to Y. There's B, there's Y. It's actually const, but you know what I mean. I get 2, 4, and boom, now I've got the values to return. Okay. So these are kind of painful, but they're really valuable in terms of just understanding in more detail what's happening when we're dealing with activation records and we're managing those activation records on the stack. And you can see this in ML, and you can see it in C. So you got an imperative language that we looked at first, a functional language that we looked at now, and in both cases you can see this notion of kind of local variables, allocate them, deallocate them as we operate from a stack. And what we're going to do now, and this is kind of the midpoint of all the material for chapter 12. Now we're going to deal with a couple of unusual cases, I guess maybe, or things that show up, which is nested function definitions and functions as parameters, and then we'll talk about long-lived activation records.